All right, well, we're back. And in this next segment, I wanted to start off with another design, another way to collect data that can give us impressions about how much characteristic changes over time. So this technique is called cross-sequential, and hopefully you recall this from the very beginning of class, but let's apply it specifically to intelligence testing. This is the strategy that the Seattle Longitudinal Study, which was initially started by a researcher called K. Warner Shea back in 1956, to study intelligence across the lifespan. Now, researchers can't just start a study in 1956 and wait, 60 years to get the data back and now publish it and maintain their research position. Like that doesn't work. So luckily, the cross-sequential design allows the researcher to, have results and publish them every, couple of years. But then also get the benefits of the long-term over the course of decades kind of pattern. So what we've got here is a little chart that's showing you kind of how cross-sequential is done. So let's say that you started the study in 1950 and you got a cohort. I'm sorry. Let's say that you started your research. You're not K. Warner Shea. You're you, and you started research in 2000. And so you recruited people who were born in 1950, 1970, and 1990 for your first basically cross-sectional design. So you test all three of these groups in 2000 and you get your results. Now you come back in 2020, and when I first pulled this chart, that was way in the future, but now it's in the past. So you come back in 2020 and now you retest the people who were born in 1970 and the people who were born in 1990, and you add a new group of 20-year-olds who were born in 2010. I didn't make this chart. Hopefully you can tell that from the graininess. I'm just doing the math here, and those people would not be 20 years old in 2020. They would be 10 years old. Something's wrong with this chart. Well, let's go on and pretend like they didn't do that problem, because those people would be 10 years old right there. And we should be testing them in. Yeah, this math's off altogether. People born in 1950 would be 50 years old in 2000. Oh man, I did not make this chart or apparently look at it that hard. I've been using it for a couple of years now. Premise is still good. So you recruit a bunch of people, you test all three of those groups in 2020. In the year 2000. Now in 2020, you come back and you retest those who are now 60 and 40 and add a new group. Now what you can start to do in 2020 is start to look at the individuals who were born in 1990 and the people who were born in 1970 and look at them like a little longitudinal study, right? You can say, have they changed? Did the 20-year-olds who are now 40-year-olds change more than the 40-year-olds who are now 60 years old? Right? Like you can start to do a little bit of longitudinal. When you come back to test again in 2040, you're going to retest the people who were born in 1990. You're going to retest the people who were born in 2010. You're probably going to be adding a new group who were born in 2030. But now look at that. You've got three dates for the three data collections for the people who were born in 1990. And now you're getting a real longitudinal picture. Was there more change between the ages of 20 and 40 than there was between the ages of 40 and 60? Is the only real difference if you were to compare them at 20 to them at 60? You're starting to get enough data to actually be able to make some pretty good comparisons. So that's the design that K. Warner Shea used, and he started with 500 adults aged 20 to 50, and every time he collects data, he adds a new cohort at the bottom, the youngest age, and keeps rotating through them. And he tries to keep following up with the oldest members as long as he possibly can, even if they're not fitting, mathematically. He tries to follow up with them over and over again. So what did he find? Well, first off, during the cross-sectional analyses, you end up with a pattern that looks like this from the K. Warner Shea data. So you're in this panel, what you're looking at is the purely cross-sectional component. And so we're looking at different groups of 25, 32, and so on. And then what we're seeing in this chart that's different from the overall chart I had shown you before is that this is taking into account lots of different aspects of an IQ test. So you've got in the purple squares, inductive reasoning. In the blue diamonds, you've got spatial orientation. Green circles are perceptual speed. Yellow triangles are numeric ability, and I don't know what that color is, periwinkle, verbal ability, and then orange is verbal memory. So what you'll notice is that if you look just at inductive reasoning, spatial orientation, perceptual speed, and then verbal memory, you'll notice that those four lines do kind of follow that cliff that I showed you in the earlier cross-sectional versus longitudinal chart. The things that don't follow that cliff pattern, even in correlational data, are numeric ability, which look pretty stable across the lifespan, and then verbal ability, pretty stable across the lifespan. It kind of increases in middle adult, stays there, and then starts to decline a little bit. But I mean, they're pretty stable. Now, if you look at the longitudinal data, you get a slightly different picture. For one thing, the overall pattern is that there's a lot more stability when you look at longitudinal data. But if you start to zoom in on it, look at the yellow triangles, which is the numeric ability. When you follow individuals across their own lifespan, now you see that numeric ability decreases across a person's lifespan, like pretty dramatically. Starting about age 50, we start to sort of drop off in our numeric ability. And then the other thing that's noticeable is if you look at the green circles, which is perceptual speed, when you go from age 25 to age 88, it's a pretty straight line down. So your fastest reaction time is going to be when you're younger, and your slowest is going to be when you get older. Like that across an individual's lifespan, it's very clear that that's a developmental effect, that literally we get slower for sure. And I think we all kind of know that. It makes me feel better that the numeric ability kind of drops off for everybody, because I got to tell you what, I keep giving the excuse that I'm doing psychology math all the time because I do the dumbest addition problems all the time. It's like, wait, that's not how you add those two numbers together. So apparently I'm losing my numeric ability just like I'm supposed to. But it's kind of interesting. It's the overall picture is that you have pretty stable intellectual capabilities across your lifespan. But even in the longitudinal setup, we can't deny that perceptual speed drops off, and we can't deny that numeric ability drops off. All right. Now, looking at this is also coming from K. Warner Shea, and this is just the same basic data, but it's comparing men to women now. So we've got slightly different colorizations of the variables that are being measured. So we've got purple is verbal, yellow is spatial, teal is inductive, red is number, and blue is word fluency. And what we're doing is comparing men to women, men on the left, women on the right. And you see that the men's drop off is more steep and starts a little earlier than the women's drop off. So there's some evidence that there are some sex differences in how intelligence changes across the lifespan. And this is longitudinal data, by the way. This is not cross-sectional. So this is within an individual. You see for both sexes, that men they kind of hit their peak a little earlier. Women on some of their variables, they hit their peak a little later, and then they maintain it a little longer than men. You'll notice spatial orientation is worse in women at all age groups compared to men. And that's something that we've seen as a sex difference for a really long time. Verbal meaning, you'll see that men get better at it across their lifespan, whereas women start off higher. But then men kind of lose it again, and women stay a little bit higher on average than men through late adulthood. So just a little bit of sex differences with regard to how intelligence changes across the lifespan. Now, something that Cattell pointed out is that there are different kinds of intelligence, like different clusters of intelligence. He said that there's this one big cluster that he called fluid intelligence, and then this other big cluster that he called crystallized intelligence. When we talk about fluid intelligence, we're talking about solving tasks that require speedy processing, whereas with crystallized intelligence, we're really talking about accumulated knowledge, right? Things that you have accumulated through learning, experience, stuff like that. So under fluid intelligence, there are three main aspects. One is the use of your working memory. Working memory is holding stuff in your consciousness and knowing that you're thinking about it, being able to manage it so that it doesn't fall out of your whatever you're focusing on at the moment. Abstract thought is another aspect of fluid intelligence. So that thing that, Piaget said we all achieve in adolescence, this ability to think abstractly. Cattell said that's part of fluid intelligence. And then the overall speed of thinking, like how quickly you can come up with answers, or how quickly you can define a word, or how quickly you can add two numbers together. Like that speed he thought was part of fluid intelligence. In crystallized intelligence, the aspects are basically, your accumulated vocabulary, knowing the words for things, and then your accumulated just general information, things that you know and sometimes don't even know why you know it, that kind of thing. General intelligence or general information. So fluid intelligence can be measured with lots of different kinds of tests, sometimes not even verbal, right? Like in this test, I don't even have to tell you what the rule is probably, and you know what you're supposed to do next. So we can measure fluid intelligence with lots of different kinds of intelligence test questions. The idea here is that you're supposed to pick up the pattern, figure out what's going on, and then what it would take to fill that blank, right? So being able to answer that more quickly is considered faster, higher fluid intelligence would be indicated by answering this question more quickly. By the way, the answer is square. This would be the kind of example of crystallized intelligence. So that vertical line between those two words means is to. So aphorism is to adage. So what is the relationship between aphorism and adage? Are they the same? Are they opposite, or are they neither? So you might be going, I have no idea what either of those are. And that's really not uncommon, right? Like that's part of the test. It's a vocabulary test. Do you know what these words mean is basically what we're trying to figure out with this setup. So if you're the sort of person like me who likes closure, an aphorism is something that we say and that we think kind of describes a situation. So for example, an aphorism would be something like, too many cooks spoil the soup. Like that's an aphorism. Some people will define it as a truism, but I'm not sure if it's true, because a lot of times we have aphorisms that contradict each other. Like birds of a feather flock together, meaning that we prefer people who are like us. But then we also have an aphorism that says opposites attract. So I'm not sure truism is a synonym for aphorism. An adage is sort of an old saying that is supposed to convey some kind of, I want to say truism again. I don't think advice is the right word, but lesson, I guess, an old adage. The old adage, when God shuts a door, he always opens a window. Like that's an adage. So now that I've given you examples, it kind of sounds like the answer might be same, right? Because they definitely are similar. I don't know if they're the same, but they are more similar than opposite, that's for sure. So what researchers have found, and what Cattell had predicted, but research has supported, is that fluid intelligence decreases with age, primarily because of that perceptual speed issue. Like as we get older, we are going to be slower at reacting. And so that means that by definition, the score is going to be lower than a younger person who's answering more quickly. But there's also some issues having to do with how the older person approaches the problem. And one of the things that happens as we get older is that we've had more experience with more things. And so when confronted with what should be a very novel problem, and that you should be able to just sort of, like in the example here, circle, square, circle blank, you should be able to just look at it and think square, right? But then you might have seen problems like this over your longer life as a middle-aged adult and say, oh, I've seen ones like this. And sometimes there's a trick, or sometimes there, you know what I mean? And so you kind of talk yourself out of the obvious, and then you try out other alternatives and finally go, no, it must be the square. Okay, I'll say square. And meanwhile, you've taken a lot more time because of your greater experience in the world, kind of interfered with your own just sort of abstract thinking and, using just the cues to come to the solution. Crystallized intelligence tends to increase with age, right? The older we are, the wider our vocabulary tends to be, the more, general information stuff we just have like tucked away in our memories. And, oftentimes just blows younger people away because they're like, how do you know this stuff? And it's like, because I've lived a long time and seen a lot of things and I've encountered a lot of things, right? So older people are more likely to enjoy playing Jeopardy, for example, or those other kinds of trivia games because they're more likely to have read the relevant book or seen the relevant play or heard the old adage or whatever, ever have heard of that author, these kinds of things, right? And so that kind of accumulated knowledge makes you better at those kinds of trivia games. So with age, crystallized intelligence improves. With age, fluid intelligence tends to go down. All right, this seems like a really good time to break. Let's go ahead and talk about Sternberg's 3 factors of intelligence in the next segment.